Chapter 11, Section 3, Key Properties of Eigenvalues and Eigenvectors, Part 2. As we saw in the previous section, eigenvalues and eigenvectors have these key properties. We saw these two properties in the previous section. This section will cover these three properties: product of eigenvalues, eigenvalues of a diagonal matrix, and eigenvalues of a triangular matrix. Let's start with product of eigenvalues. This property says that for a square matrix A of size n by n, the product of the eigenvalues of A is equal to the determinant of A. Let's take an example. For this matrix A, the eigenvalues are lambda 1 equals 7 and lambda 2 equals 1. The determinant of A equals 7. The product of eigenvalues lambda 1 by lambda 2 equals 7 by 1 equals 7, which matches the determinant. Let's prove this property mathematically. The eigenvalues of A are defined as the roots of the characteristic equation. As we saw in the previous section, the characteristic polynomial can be factored in this way. Here, lambda 1, lambda 2, lambda n are the eigenvalues of A. By setting lambda equals 0, we can simplify the characteristic polynomial. This result shows that the product of eigenvalues of A equals to the determinant of A. The next property is about eigenvalues of a diagonal matrix. For a diagonal matrix D, the eigenvalues are simply the entries on the diagonal, and the eigenvectors are the standard basis vectors. This is because multiplying a diagonal matrix by a standard basis vector scales the vector by the corresponding diagonal entry. As an example, take this diagonal matrix D. One of its eigenvectors is E1, and in this case, the eigenvalue is 3. Another eigenvector is E2, and in this case, the eigenvalue is 5. As we can see, each diagonal entry of matrix D corresponds to an eigenvalue, and the standard basis, that is, E1 and E2, are the eigenvectors. Let's prove this property mathematically. A diagonal matrix D can be expressed in this way. Here, the diagonal elements D1, D2, Dn are real or complex numbers. By definition, an eigenvalue lambda and its corresponding eigenvector v satisfy this equation. For a general vector, the matrix multiplication results in this vector. Since dv equals lambda v, this equation holds. This implies that each component satisfies the following equation. So, if vi is not equal to 0, lambda equals di. And if vi equals 0, the equation holds trivially. Thus, the eigenvalues of diagonal matrix D are the diagonal elements D1, D2, Dn. Finally, let me show that these eigenvectors are standard basis vectors. To find the eigenvectors, we need to solve this equation. For lambda equals dk, the matrix D minus lambda I has zeros everywhere except for the kth diagonal element. For a non-trivial solution to exist, at least one component vk must be non-zero. By choosing vk equals 1 and vj equals 0, for all j is not equal to k, we obtain the standard basis vector. Here, the 1 is at the kth position. Thus, the eigenvectors of D are the standard basis vectors, Ek. The next property is about eigenvalues of a triangular matrix. For an upper or lower triangular matrix, the eigenvalues are also the entries on the main diagonal. This is due to the determinant of a triangular matrix being the product of its diagonal elements. As an example, let's consider this upper triangular matrix A. Step 1. Eigenvalues and the determinant equation. To find the eigenvalues of A, we solve the characteristic equation. Here, lambda is the eigenvalue and I is the identity matrix. Step 2. Substitute A minus lambda I. Subtract lambda from each diagonal element of A. Step 3. Determinant of a triangular matrix. The determinant of a triangular matrix is the product of its diagonal elements. Step 4. Solve for eigenvalues. Set the determinant to 0. From this, the eigenvalues are lambda equals 2, lambda equals 3, and lambda equals 5. The eigenvalues of the triangular matrix A are exactly the entries on its main diagonal. This result holds for any upper or lower triangular matrix because the determinant simplifies to the product of the diagonal elements. The determinant involves multiplying diagonal entries when the matrix is triangular. Subtracting lambda only modifies the diagonal entries, and all off-diagonal elements remain unchanged. As a result, the eigenvalues of a triangular matrix are always its diagonal elements. Let's prove this property mathematically. Let T be an upper or lower triangular matrix. First, let's assume T as an upper triangular matrix. A similar proof holds for a lower triangular matrix. The eigenvalues of T are the roots of the characteristic equation. Subtracting lambda I from T, we obtain this matrix. Since T minus lambda I is still upper triangular, its determinant is simply the product of its diagonal elements. This polynomial's roots are T11, T12, Tnn. Thus, the eigenvalues of T are its diagonal elements. If T is a lower triangular matrix, T minus lambda I is also lower triangular, and its determinant follows the same pattern. Thus, the eigenvalues are still the diagonal elements. As shown above, for any upper or lower triangular matrix, the eigenvalues are exactly the diagonal entries. Thank you for watching. Please thumbs up and subscribe to my channel.